let us look at 13.52. Let's solve for solutions A and B. We're gonna calculate the rest as a class tomorrow. So we want to complete this table. So for solution A, you're given the solution has a pH of 9.63, and you can determine what pOH is. Remember that pH plus pOH is equal to 14. Okay, so pH plus pOH is equal to 14. Okay, so here you can actually just calculate pOH by subtracting 9.63 from 14. So that's 14. pOH is equal to 14 minus 9.63, and that should give you 4.47. Okay, and then after that you have the concentration of H plus. Now again, keep in mind that pH is equal to the negative log of the concentration of the proton. Okay, so therefore negative pH, and for pOH that's H minus is equal to 10 to the negative pOH. Okay, so for this one we have 10 to the negative 9.63 for H plus, 10 to the negative 9.63, which is just equal to 2.3 times 10 to the negative 10 molar. Okay, now for this, I'd like to introduce to your rules for logarithms. Okay, if you are actually getting, or if you want to figure out how many significant figures you should express for this answer which is, by the way, an exponential number, the number of sig figs here is determined by the number of sig figs in this number, the number after the decimal. Okay, so this number is actually called the mantissa. Okay, and 9 here is actually called the characteristic. Okay, so again here the answer for 10 to the negative 9.63 should have 2 sig figs because there are 2 significant figures in the mantissa. Okay, you can calculate next for OH 2 different ways, either 10 to the negative pOH or using the autoionization constant of water. But let's do it an easier way. So that's 10 to the negative pOH, so this is going to be 10 to the negative 4.37. And this one will just be equal to 4.3 times 10 to the negative 5. Okay. Now, last time I checked, negative 5 times 10 to the negative 5 is a greater concentration than times 10 to the negative, than 2.3 times 10 to the negative 10, so therefore this should be basic. Okay, now for this next problem, we're given the concentration of OH. Okay, now here for the concentration of OH, remember that we can solve this again a lot of ways, but I'd like to do this in a sense that let's start first with this concentration, knowing again that H plus times OH minus, okay, is equal to 1.0 times 10 to the positive 14 molar squared. Okay, using the concentration of H, we can actually solve for OH minus rather. We can solve for the concentration of H plus. So that should just be 1.0 times 10 to the negative 14 to the negative 14 rather. Okay, molar squared divided by 3.9 times 10 to the negative 6 molar. So this should give you for the concentration of H plus 2.6 times 10 to the negative 9. 2.6 times 10 to the negative 9 molar. Alright. Now, from here, we just take the negative log of the concentration of H plus and OH minus to get the pH and pOH respectively. So here, for pH, that's going to be equal to negative log of 2.6 times 10 to the negative 9, okay, molar, and this should actually be equal to 8.59. Okay, now let's discuss sig figs here again. So here, the number of significant figures, okay, in the number that you're getting the logarithm of, in which case here 2.6 that has 2 sig figs, okay, the number of sig figs there will be equal to the number of digits in the mantissa. Again, the digits after the decimal point will be equal to the number of significant figures after the mantissa. So here you have 5 and 9, which are significant. That's why the answer is 8.59. So this one should be 8.59. Okay, and then POH is just PH minus, and then POH is just 14 minus PH. So 14 minus PH is equal to 14 minus 8.59. So this should be 5.41. And this one is still a basic solution because the pH is above 7. Now, in the next problems, we are going to actually look at the pH values of strong and weak acids. I'm going to post another video of how the pH is calculated for strong acids. In particular, we're going to do strong bases in class, and then we're going to do weak acids and weak bases in class as well.